Take a look at your cheat sheet where it says the rules of electron configuration. This is going to take us into our first of 3 notations for showing where the electrons live. We're also going to be trickling on to the back of that cheat sheet today and using the new one, secondary cheat sheet that you've received. Whenever we look at the orbitals that are going around that nucleus, again, that's just the nucleus. The orbitals actually take a variety of shapes. It's a 3D model is what's important for you to understand. If I was holding right now an atom of hydrogen, well, it could have an orbital that's going around in a circle, the way that I could draw it on the whiteboard behind me, but it could also have an orbital that's coming like this at you, right? Because this, I only have 2 dimensions here. If we were living in our dimensional world, I could have an orbital coming at you, or I could have one going at a diagonal. And the way it works is looking at the periodic table, pretty much the further down you get from top to bottom, the more complex those orbitals get. Whenever we're showing electron configurations, there's going to be a couple things. There's going to be what's called main energy levels. You write this with me. And the main energy levels will be represented by numbers. It'll be a number 1 through 7. Bear with me as we tiptoe into this. You'll start to see how we apply these things soon. Not only do we characterize an element by its main energy levels, we also characterize it by its sublevel. But sublevels are not represented by numbers. Instead, they'll be represented by letters. Either S, D, sorry, I should have gotten P next, P, D, or F. This already has implications of questions I can ask you. If I give you a random element like nitrogen and I say, what sublevel does nitrogen go up to? Some of your choices will be numbers, but if I ask about the sublevel, well, the answer can only be letters. So I want your brain to start differentiating early, even though you don't even know what this stuff means yet. But main energy levels are numbers, sublevels are letters. Now, if you take a look at your cheat sheet, you'll see the letters S, P, D, and F explained in a little bit more detail. It says that S can hold 1 orbital, that P can hold 3, D5, and F7. Just reading that off your cheat sheet, but it's good for your brain to write it again. These numbers apply to that idea of some elements just have 1 orbital, 1 simple orbital, while others, like the F that has 7 circles flying around it, is much more complex. So remember, the orbitals are those circular pathways where the electrons live. So if we're dealing with an element that lives in sublevel F, well, that means it's got 7 different circles flying around it. It would be a much more complex element than one that lives in the S sublevel, which would just have a single circle around it. Yes, sir?
Why are they all odd numbers?
That's more of a nature question. That's like asking me why the sun appears to be yellow. It just does. They just do. Sometimes that's a science answer, believe it or not. So let's apply this to an actual element. I'm going to erase this, but of course all this information is accessible sitting at the bottom of your cheat sheet. Because here's what our real goal is. I'm going to give you an element. It can be any element on the periodic table that I want it to be. For example, I'll start off by saying we'll do fluorine. Write down fluorine. Somewhere where you've got lots of space in your notes. Now, we're going to look at the energy level, numbers, and the sublevel, letters, of fluorine, a random element that I chose off the periodic table. But remember, it's electrons that we're looking at. So before we start this new process, how many electrons does fluorine have? It's got 9. Now, if for some reason you've forgotten, the number of electrons is equal to the atomic number, ultimately. It's equal to the number of protons, which is equal to the atomic number. So just by looking at the top number in fluorine's periodic table square, I know that fluorine has 9 electrons. So that's important information to know because it's electrons that we're going to be dealing with. In orbital notation, the long one that we're about to do, there's some pictorial things that you need to know. We're going to draw a pretty little picture. But I need to set up a legend for you real quick. So over to the side of your notes, kind of in the margin, every time we draw a line like that, an empty line that can have room to go have stuff on top of it, that's going to represent an orbital. And in the picture we're about to draw, every time we draw an arrow, yes, that's an arrow. Some of y'all don't think it's an arrow. All right. You think that's an arrow. It is, but we're about to draw hundreds of arrows. So you'll do a lot less work if you only draw one flag on it. You can draw 2 flags on your arrows. I don't care. But every time we draw an arrow, that's going to represent an electron. So that's our key off to the side, and you'll see how we'll apply it to orbital notation in just a moment. Take a look at your new cheat sheet, the one that looks like this. You'll want this in front of you. In order to draw the orbital notation of fluorine, we've got to learn some things about this new cheat sheet. We're going to start off with Aufbau's principle. And Aufbau's principle states, electrons always occupy the lowest energy level first. Look at this new cheat sheet. Remember, the energy level is numbers. Do you see how this cheat sheet is a perfect overlay of your periodic table? For every square on your periodic table, there's a square on this sheet. So you can actually pinpoint fluorine's square on this unlabeled periodic table. But not only that, do you see how there's letters and numbers? Do you see the numbers and the letters on here? What are those numbers? They're main energy levels. If you look back to stuff I've already told you, what are the letters? They're sublevels. Now, our first rule, Aufbau's principle, says that no matter what element we're going to configure, we're always going to start in the lowest energy level. What's the lowest energy level that you see on this paper? 1. Remember, energy levels are numbers. 1 is the smallest one here. So here's what it says. That's hydrogen, right? Isn't that hydrogen that lives in that square? You can verify. Look on your other periodic table. That's hydrogen's square. No matter what element we're going to configure, we're always going to start up here at hydrogen. So let's write that down. Write down 1s. Because that's where we are always going to start. 1s. Hey, what letter did I write? It's an S. Now, a moment ago, we talked about how many orbitals, which we're going to represent with blank lines, how many orbitals an S has. How many orbitals does an S have? Look back at your cheat sheet if you don't know. 1, look where I'm looking. I don't want anybody to be confused. S has 1 orbital. So right above the 1s, watch what I'm going to do. I'm going to draw 1 flat line. Because remember, that 1 flat line represents an orbital. So I've shown S is 1 orbital. Looking at our cheat sheet, we have our second rule. It's called Pauli's exclusion principle. Let's see what that says. It says 2 electrons of opposite spin can occupy an orbital. For every one of these lines we draw, we can put 2 electrons on it, spinning opposite directions. Remember, they're spinning around that nucleus, but they actually spin in different directions around that nucleus. So, let's put our 2 electrons. It says for every line, we can put 2 electrons. 1. Remember, the arrows represent electrons. 1. Uh-oh, it said the other electron should be spinning the other way. How do you think I can show that? Yeah, let's point the other one down. Now I know this feels really weird and you're not really sure what's going on. You're going to catch on, I promise. Keep bearing with me. How many electrons have we drawn total so far? How many electrons do we need to draw for fluorine? 9. We're not there yet, so let's keep going. Look at your table. The way that you're going to know what comes next is you're going to read this table the way you read a book. You're going to go to the very end of the line and then go down to the next line. Go to the very end of the line and go down to the next line. What comes after 1s? And don't say 1s. What comes after 1s? It's 2s. All right, yeah, helium's over there, but he was part of my 1s. After 1s comes 2s. So write down 2s. And now the questions will start to become repetitive. How many orbitals does an S have? No. Listen to my question. Not 2. How many orbitals? Just 1. And if you don't know why, look back over here. S contains 1 orbital. It's right there. Boom, 1 orbital. Remember, those flat lines represent orbitals. How many electrons can fit in an orbital? 2. Remember, Pauli's exclusion principle said that for every time you draw one of those lines, you can put 2 differently spinning electrons in the orbital. How many electrons have we drawn total now? 1, 2, 3, 4. Are we done? No. Fluorine has 9. We've got to get to 9. So, let's continue. Now, we're at 2s right now. If we read straight across to the other side, what comes after 2s? 2p. Does everybody see that? Remember, we're reading it like a book. After 2s comes 2p. Now, this is the first time that we've done a p. The questions are the same, but the answers are a little bit different. How many orbitals does a p have? 3. Look on your cheat sheet if you don't know where it says p has 3. Watch what I do. Watch. 1, 2, 3. Remember, every one of those lines is an orbital. P needs to have 3 orbitals. 1, 2, 3. Yes, sir.
So we skip the second 1s.
Well, we're not skipping the second 1s. It's just the way that the table's set up. It confuses your brain, but that 1s you can just imagine is over there right next to it, like all the other s's. If you run your eyes down the table, all the s's are right next to each other, right? And they're all made of 2 squares, except for 1s. Sorry, all I can do is apologize about that. Imagine that other 1s square is over there also. Now, there's one more rule on your cheat sheet that we haven't covered yet. It's Hund's rule. Let's read that. It says, if there is more than 1 orbital in a sublevel, which is true for all the sublevels except for S. If there's more than 1 orbital, 1 electron will go in each of them before you double them up. Let's see what that means. How many electrons have we drawn so far? 4. How many more do we need to get to 9? We need 5 more. We need to draw 5 more electrons. Watch the funky way I'm going to do this. 1, 2, 3, 4, 5. Hund's rule stated that I need to put one electron in each orbital before I put a second one in any of them. Up, 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 down, down. But we didn't do that last one because that wouldn't be fluorine, that would be neon. 1, 2, 3, 4, 5, 6, 7, 8. We've drawn 9 electrons. This is the orbital notation for fluorine. Crazy? Now, your brain's probably a little fuzzy, and that's okay. You're going to really catch on this next example. Find titanium. Now, make sure you're writing everything in your notes that you can so that when you do your online assignment, you can come back and look at the exact process we go through from start to finish. Because I always ask the questions in the exact same order. Question number 1, after we know our element. How many electrons does titanium have? 22. So right now we know that we're going to draw 22 of those. That's our goal. If we draw 22 arrows, we're done. And now we've got our rules, Aufbau, Pauli, and Hund. Remember, one of them says always start where hydrogen is. One of them says you could put 2 arrows in every orbital. And the last one says that if you have multiple orbitals in a single sublevel, put 1 in each before you double them. That's all the rules of this. So let's do titanium. We always start there, right? So put 1s. And here come the questions. How many orbitals does an S have? 1. It's got 1. Verify that on your cheat sheet. How many electrons can fit in that one orbital? 2. The answer is always 2 to that question. One orbital can always hold 2 electrons, but they must spin opposite directions. Read your book on your other cheat sheet. What always comes after 1s? 2s. Anybody not see why 2s comes next? All right, 2s. How many orbitals does an s have? Just 1. That's always the answer to that question. S is always 1. How many electrons can fit in that orbital? 2. What comes after 2s as we read on our book? 2p. Hey, you know what? If you look at our previous example of fluorine, this stuff's going in the exact same order, isn't it? It always will do that. Some of y'all will even accidentally memorize the order just because it's so repetitive. How many orbitals does a p have? It's got 3. All right? Look on your cheat sheet. It says that p's have 3 orbitals. So there they are. But what's the trick here? 1 in each one, up, 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 before you go back and double them. Down, down, down. Now, some of you that think you're smart will look at that and be like, how will you know the order I draw them in? I could have gone up, down, up, down, up, down, and it would look the exact same right now. You're absolutely right. I would have no way of knowing if you drew them in the correct order. But if you don't know that rule, you can still really mess up the very end of a configuration. I'll show you what I mean in a moment. Now, we haven't gotten this far yet. Hey, what element is that? This is the orbital notation for a element. It's not titanium. What element is that? It's neon. If I would have said, hey, draw the orbital notation for neon, that would be the final answer. 2, 4, 6, 8, 10. Neon has 10 electrons. But we need 12 more. 10 to 22 would be 12 more. So let's keep going. What comes after 2p? 3s. Remember, we're reading it like a book. 3s. 1 orbital. I like it when someone knows what I'm about to ask. How many orbitals does an s have? 1. How many electrons fit in an orbital? 2. Make sure they're spinning opposite directions. After after 3s comes 3p. How many orbitals does a p have? 3. All right, now keep count of your arrows. 2, 4, 6, 8, 10, 12. All right, not there yet. Up, up, up. 13, 14, 15. Down, down, down. 16, 17, 18. Still not there. Yes, sir.
So does the number before the sublevel count?
Okay, so the number before the sublevel is telling you the energy of those electrons. The higher that number, the more energy those electrons are holding on to. It has no direct connection to how many arrows or anything like that. It's just titanium, compared to our first example, has electrons with more energy because we're about to get to a bigger number. What comes after 3p? 4s. Everybody see why 4s comes after 3p. Don't suffer in silence. Here's our question. How many orbitals does an s hold?
1.
How many electrons can go in there? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We're close. How many more do we need? We need 2 more. We need 2 more. So let's keep going. What comes after 4s? 3d. Ooh, we haven't done a d yet. Are you excited? You're excited. 3d. Leave yourself some space because this guy's a little different. 3d. All right. Those movies cost more money, right? Because you wear glasses. Okay. How many orbitals does a D have? 5. Again, that's not brain surgery. I mean, yeah, you'll have to have it memorized for the test, but 5 orbitals. 1, 2, 3, 4, 5. Draw all of them. Yeah, I know, we only need 2 more electrons, but we do this in the same order. 3D has 5 orbitals. And here's where Hund's rule can really mess you up. We only need to draw 2 more, right? If you do this, it's game over. You've missed the entire thing. That's not what it looks like in nature. All right, think about what you're drawing. Every one of these lines represents a circle, a circular path around the nucleus. And in nature, if you go and look at titanium, on its outermost area, there's 5 circles there. And there's only 2 electrons on them, but they're on different circles. They're on different orbitals. Which is why we have to draw it like that. Up, up. This is the orbital notation for titanium. Yes, a bunch of empty spots. All right, if we would have needed 1 more, if we would have gone to vanadium, well, then there would have been 1 more up, and that would have gotten us to 23. The path is always the same. You're always going to go through these exact steps, no matter which element you're configuring. The only difference between examples is where you stop. Look at your real periodic table and put your finger on titanium square. Put your finger on titanium square on your real periodic table. Now slide your new cheat sheet and put your finger on titanium square there also. You should have a finger on 2 different squares, well, on 2 different pieces of paper, but the same square. Do you see how before we even started this stupidity, that I could figure out that titanium is the 2nd square in the 3D block? Do you see what do you say? Listen to my words. Titanium is the 2nd square in the 3D block, yes? So before I even started, if you didn't want to be obsessed with counting arrows, you could just tell yourself, you could write yourself a little note, hey, when I get to 2 of those in the 3D block, I know to stop. 2, it's square number 2 in the 3D block. So some of y'all like to think about things like that because it will become easier if you do so, but it's kind of like a little cheat. Oh yeah. Oh yeah. Last example. Draw the orbital notation for indium. See how far you can get. Indium is element number 49. Draw the orbital notation for indium. If you need my help, call me over.